Here. Notice I have my friendly calculator with me. Where's yours? In class we talked about this problem here where this is a compound factor or a growth factor we called it. And so we would invest a present value of, I believe we put $100 in the bank at 5% for 1 year, and we solved that to be $105, then reinvested for another year at 5% and wound up with $110.25. You can review your notes on what part is the principal, what part is the interest each year, and which part is the interest on interest. Well, suppose that we relax our assumption that we're only going to compound once a year. So we add this new n here into this equation. And in equation 1, n is equal to 1. So 1 plus r divided by n is r, and an n of 1 times t is t. But many banks and many investments offer compounding more than once a year. So what I've done is I've set up this table here for us, r and result period. So r is 5%. If we used Excel and to format it, say 5%, but we use 0.05 because it's a calculation. Here's n, and then we run it through equation 2. Here's the result. No surprise, because we did that one in class. If we compound every 6 months, n would be 2. If we compound every quarter, n is 4. If we compound every month, n is 12. And we're assuming t is equal to 1. We're using this equation with t equal to 1. We see the factor grows, but it starts to slow down its growth. Notice that when we go to weekly compounding, it grows, but only out there in the 4th decimal place and beyond. When we go to daily compounding, interest factor changes out there in the 5th decimal places. We go hourly. Again, it changes out there in the 5th decimal spot. And if we go to the minute, 525,600 is the number of minutes in a year, we get 1.0512, etc. It changes out way out here in the 6th decimal place. Well, you can imagine we can continue this and let n get very big. Now, you might think 525,000 is very big, but we can take the minutes and do what? Well, we can compound by the second, and then by the half second, the quarter second, a tenth of a second, a hundredth of a second, etc. So n gets very big. It can get very big. It's a finite number, but it's nowhere near as big a finite number as we can think of. This expression here, don't let this one fool you. E to the RT. On our calculator, you'll see that we have a button called e raised to the x. And that's the second. You have to use second, and you'll see the ln button. And that says raise this number e to this rt, or we can put x in as rt, rate times time. And rate here will be 0.05, t is 1. So e to the 0.05 is 1.05127110, and you can verify this on your calculator. What this is here is this is continuous compounding, meaning that we've taken any interval you can think of and divided it into an infinite number of parts. So this factor e to the RT is another way of saying this is a growth factor. It's very easy to use because the R is always annual, and t is the number of years. So we don't have to worry about dividing by n and then multiplying n times t. This discrete expression here can be replaced by this continuous one down here. So in our problems in class, we will have problems that say, assume monthly compounding, assume daily compounding, assume weekly compounding, or assume continuous compounding. And really, continuous compounding is very easy to use. But I hope this example shows you that e to the RT, where r is 0.05, t is equal to 1, results in a number that is very close to what we get with this discrete example when n is 525,600 and t is equal to 1. You can see it just changes out there just a little tiny bit out there in the 7th and 8th decimal places. So I hope this helps you understand how to adjust an annual rate by the number of compounding periods and then create this new compound interest factor. I'll see you later.